So then about drying, we said all these slurry or paste-based system, they contain some solvent which needs to be removed by so-called process of drying. Casted or plastically formed part needs to be dried to remove the solvent. You don't really remove polymer, you are only removing water or some other organic solvent. Okay, before subsequent binder removal. Binder removal, you are trying to remove the polymer and sintering to bond the particles together. But one important step of drying, casted or extruded content typically contain 20 to 30% of solvent by weight. And the more solvent, the larger the shrinkage just by the capillary force. Okay. Here we see typical drying depending on how much moisture or solvent content. Sometimes it has so-called a multi-stage drying. Here I'm showing a multi-stage drying. The vertical axis is rate of water loss. It's essentially how fast the solvent leaves your green body. The horizontal axis is water content in your so-called body, green body, right? So initially, when the water content in your gel is high, of course not 100% high, your rate of water loss would be initially high. But then, as you have less and less so-called water content in your gel, the rate of water loss would naturally decrease. Make sense? You are getting drier and drier. Of course, the rate of losing water becomes lower and lower. So this stage people can call so-called constant rate period, or CRP. Okay. Liquid essentially covers almost the entire body surface. Okay. It dries relatively fast. Powder compact in this stage would shrink in so-called overall size due to capillary force. The water is leaving, it's pulling everything together with it so that every powder comes closer, exerted by the liquid. Make sense? And then, so-called falling rate period, FRP, falling rate period. In this period, the moisture content or solvent content is much lower, and quite often there would be no further reduction in compact size because after certain point, the powders would start to already touch each other without sintering. Just by solvent removal, you cannot make the particles pack denser. Make sense? So not much further reduction in compact size because the particles are already touching each other, unlike they are suspended in the slurry or suspension. Make sense? And then there will be a gradual decrease in evaporation rate. Okay? The drying shrinkage, very important. Here we're showing volume shrinkage versus moisture content, assuming we are using water, as well as rate of drying, which is how fast we are removing water versus the moisture content. Let's first look at the shrinkage curve. Shrinkage curve. Which is this way, right? Shrinkage, volume shrinkage. If the body has more moisture, it would have higher shrinkage. On the other hand, when the moisture content decrease to a certain point, the shrinkage beyond that would be very small because beyond here, essentially each individual particles are already packed reasonably dense. And further water leaving the system or moisture leaving the system, it's just they're evaporating away from the pores. You cannot cause the particles to come any closer. Make sense? That's not enough driving force. The shrinkage is larger when the solvent content is higher than roughly 20%. Make sense? The shrinkage is small or essentially null when the solvent content becomes less than roughly this point, because they are essentially particle touching. And the other side is about rate of drying. Rate of drying. Not surprisingly, when the moisture content is high, your rate of drying is here. You are reading towards the right side. Your rate of drying is fast, and your moisture content decrease. The rate of drying also decrease. Towards the end, you have very little moisture, your rate of drying, which is how fast you are removing solvent gram per unit time, decrease almost to zero because you do not have much solvent left. Make sense? Okay. And then drying, if you ever handle ceramic, you find it's a lot of complication. Looks simple, just like when you cook. Looks simple, but sometimes you have all types of defects. Capillary action in drying, which if not controlled well, may lead to non-uniformity or severe cracking in your green body. Okay, here we are giving the schematics. We have the ceramic body, but then some portions still have liquid, some portions have kind of like semi-dried, have solvent in between them. And you can imagine the solvent in this bead of slurry will evaporate at one time. At the same time, they are going to suck into the neighboring dried region, and that capillary force can be significant, okay, if not controlled well. And similarly, if we have mold, if we have slurry or suspension, at the surface we would have particle packing, and the solvent would continue to migrate or sucked into the mold. And if we are not controlling it well, the capillary force can cause cracking in the sediments. The drying defects, deformation such as bending, which can come from all types of unsymmetric symmetry or non-uniformity. Here we have higher vapor pressure on one side, lower pressure on the other side. It may cause to bend. We have finer particle on the top, coarser particle at the bottom. Make sense? Because when you have sediment, the larger particles quickly go to the bottom. The finer particle take a longer time to settle, and of course your packing will not be very uniform. And the drying, during drying, you may also already to see these types of warping or bending. Make sense? And then crack formation. Locally concentrated stress due to the capillary force can cause cracking. And there are different ways to so-called mitigate or reduce the drying defect. For example, do it longer time. Be more patient, right? Let it happen so that you are not causing the green body to change shape too quickly. Okay. Even dry in hours or even days for large body in production. When I was visiting a white well, they were doing toilet. They said, okay, our drying of our toilet really takes several days. A big toilet, right? It takes time for it to dry completely. Increased particle size, not very practical. Increased particle size, essentially we are making the capillary force smaller. The liquid can go, not enough shrinkage. Yeah, right. And then increase drying temperature. Increase the drying temperature. At the same time, maintain high humidity, which increase the temperature to decrease the viscosity of your slurry. And make also your polymer, if you have remaining polymer, makes the polymer also soft, more plastic, to enable it to move. Okay, and higher humidity if you are using water.